Here we introduce the mechanical energy of a system and show the circumstances under which mechanical energy is conserved. A system may include objects and may also include conservative interactions or conservative forces. And you are free to choose what to include in a system. It's always up to us what's in and what's out. So the mechanical energy, represented by capital E of a system, it is the sum of one kinetic energy term for each object included in the system, and one potential energy term for each conservative interaction included in the system. So in equation form, we say E equals the sum of all the kinetic energies plus the sum of all the gravitational potential energies in green, and plus the sum of the spring or elastic potential energies here in red. Each UG term typically represents an object-Earth interaction via gravity. And you may need to choose a vertical reference point to express gravitational potential energy. Pick a location where y equals 0. Each US term typically represents a spring-like elastic interaction either between an object and a fixed surface, like here, this cart and this spring between the cart and this fixed wall here, or between an object and another object, like this spring here attached to the cart will mediate the interaction between cart A and cart B when they bump into each other. So now that I've introduced this scenario, let's look at it more closely as an example, illustrating how we could define mechanical energy. I've got two carts, cart A and cart B, at one particular moment in time along this curved track. Cart B rolling this way. Cart A is currently moving to the right and being pushed to the right by this compressed spring P here between the cart and the wall. Spring Q is attached to cart A, but it's not compressed or stretched at the moment. It's just being carried along with it. I've indicated that this is the location of spring P's right end when it is at its natural unstretched length. So currently spring P is compressed by this displacement here, xp1. This is moment 1, so I'm calling it the displacement of spring P at moment 1, xp1. Here's the velocity of cart A at moment 1. And if I set my reference point for gravitational potential energy purposes, y equals 0 down here, then the center of mass of cart A is located a distance ya1 above that reference point at this moment, a value that we'll need to use to express the gravitational potential energy of cart A at this moment. Cart B over here also has a center of mass that is a height yb1 above our reference point at this instant. So at this moment in time, we can write down an expression for the mechanical energy of this system. Here it is. It will include one kinetic energy term for each cart, one gravitational potential energy term for the interaction between each cart and the Earth. The cart and the Earth, each interaction gets its own term, and then one spring potential energy term for each spring P and spring Q, spring P and spring Q, that could be mediating an elastic interaction between objects. So at moment 1, let's get more specific about each of these terms. Any object that is moving, that has a speed, has kinetic energy. So the kinetic energy of cart A is 1/2 mv squared, ma, the mass of cart A, times the speed of cart A at that moment squared. That's our Ka term. Add to that the Kb term, 1/2 mass B times Vb at moment 1 squared. Then the UG terms, each of these is mgy. So the gravitational potential energy of cart A here, mass of A times little g times the height ya1 of the center of mass above our reference point. So that's mgy for this cart. Add to that mgy for cart B, that'll be this term. So all 4 of those terms are non-zero because we have a speed, so we have non-zero kinetic energy, and our objects are located above the reference point. So they have some height above the reference point, so they also have non-zero UG. Now, as for our springs, one of them is compressed at this moment, spring P, so it's storing spring potential energy. That'll be given by this expression, 1/2 kx squared. K, the stiffness of spring P, and then xp1, the displacement of spring P from its natural unstretched position. 1/2 kp xp1 squared, that's the elastic potential energy being stored in this spring at this moment. Spring Q, however, is at its natural length currently. It's not compressed or stretched. So the X for Q at this moment would be 0. It is not displaced. Therefore, spring Q is storing no elastic potential energy. That term would be 0. The other 5 terms would be non-zero at the moment. So there is the mechanical energy of this system at moment 1. Let's look at a later moment in time. Suppose spring P launches this cart in this direction. It collides with cart B. The spring Q between A and B causes them to repel off of each other. Spring B gets turned around and launched back to the right. Spring A will get reversed and launched back to the left. And this could be our situation a short time later at what we'll call moment Q, post-collision after A and B have pushed off of each other via spring Q. So B's heading off this way, A's heading off that way at moment 2. Let's write down an expression for the mechanical energy of this system at this moment now. There is a Ka term and a Kb term. There is kinetic energy for each cart because each cart is moving. If you're moving, if you have a speed, you have kinetic energy. We have a UG term for each cart as well, because each cart is at a location that is not the reference point. They're both above the y equals 0 reference point, so they both have gravitational potential energy, mgy for A and mgy for B at this moment. However, both springs, spring P and spring Q, are back at their natural length at this instant. Spring P is not compressed or stretched. Spring Q is not compressed or stretched. Therefore, the displacement xp and the displacement xq are both 0. So there is no spring potential energy, no elastic potential energy at this instant. Both those terms are 0. So we have 4 non-zero terms and 2 zero terms for the mechanical energy at moment 2. This is all well and good. We can write down an expression from the mechanical energies at these 2 moments. But then the natural question would be, well, how is E2 related to E1? How are the mechanical energies at these 2 moments related to each other? And so we're about to show that. Starting with the work energy theorem, here comes a derivation of our conservation of mechanical energy principle. Start with the work energy theorem. A work energy for cart A, add to that work energy for cart B. This is then the net work on the system, the sum of all the works on A and the sum of all the works on B. This is from moment 1 to 2, so the work's done on cart A and cart B between those 2 moments. The sum of all those works, which will then be the net work on the system, sum of all the works on each object in the system is the net work on the system. That'll be equal to the change in the kinetic energy of A plus the change in kinetic energy of B. Now, the network on the system, I'm going to split into 2 categories. WC will represent the network, even though I'm not using a capital sigma here to show a sum. WC we're going to understand to be the network done by all conservative forces in the system. And WNC will be the network done by all non-conservative forces in the system. So I'm splitting up all the work done into these 2 categories, the work done by the conservative forces plus the work done by the non-conservative forces. And let's look at the work done by the conservative forces. There are 4 conservative interactions here: gravity on A, gravity on B, spring P, and spring Q. So there's work done potentially by each of those 4 conservative forces. And we know that the work done by a conservative force is equal to the opposite of the change in the corresponding potential energy. Work done by gravity equals the opposite of the change in UG. Work done by an elastic force is the opposite of the change in the elastic potential energy US. So we're going to replace WGA with minus delta UGA. WGB with minus delta UGB, and likewise WSP with minus delta USP, WSQ with minus delta USQ. So the work done by the conservative forces equals the changes, the sums of the changes of all of these potential energies in the system. So that goes in here for WC. That's something for WC. Add to that WNC, the work done by non-conservative forces, and the sum of those two things should equal the change in the kinetic energy of A plus the change in kinetic energy of B. That's here now. Our next move is to just rearrange these terms here. I'm going to add all of these delta U's over to the side with delta K's, and then flip the two sides. That'll get us here to this line, where we've got delta K plus delta K plus delta U plus delta U plus delta U plus delta U equals WNC. We've got the work done by non-conservative forces isolated all by itself over here, the net work by non-conservative forces. That's by itself. We show that that is equal to the sums of all these changes of kinetic energies and gravitational and spring potential energies. Next thing to note is that the change in mechanical energy of the system is the E final minus E initial. So here's E final, that's sum of terms, minus an E initial, so this sum of terms. And if I line them up, I can take Ka final minus Ka initial to get delta K, Kb final minus Kb initial to get delta Kb, and so on. Uga final minus Uga initial to get delta Uga. And in that way, demonstrate that the sum of all these changes in kinetic and potential energies is identical to the change in the mechanical energy of the system. So look at that sum of changes. That's what we have right here. Therefore, the whole left-hand side of this equation equals delta E, the change in the mechanical energy of the system. And we've arrived at this valuable result. This equation is called the conservation, or it represents the conservation of mechanical energy. The change in the mechanical energy of a system over some time interval, between two events, is given by the work done by any non-conservative forces that are present between those two events. And in particular, if the work done by non-conservative forces happens to be zero, then delta E is zero between those two moments, which would mean that E final equals E initial. And that's the answer then to our question above here. How might the final mechanical energy be related to the initial mechanical energy? Well, if no work was done by non-conservative forces during that time interval, then those two energies are equal, which would allow us to set our expression for the mechanical energy at moment one, at this instant, equal to the mechanical energy of the system at moment two, that instant. So all of this set equal to all of that, a valuable result that we could then use to potentially solve for something here that was an unknown.